Okay, this is 6.1, the law of sines. And, zoom in. Okay, don't forget that this is every other even 2 through 42. Now, basically the law of sines looks like this. It looks like there should be 3 parts to it, but actually this is just a short way to have kind of 3 equations in one. So this would be one equation. This would be another equation. And then that would be the third one right there. Okay, so you're choosing any 2 out of these 3 to equate to one another to solve, to find your unknown value. Okay, so what is the law of sines applicable to? Well, a lot of what we've been doing in pre-calculus is focusing on right triangles. That is, triangles that have a 90-degree corner in them. All the other triangles are called oblique triangles that don't have 90-degree corners in them. So they either have 3 acute angles, like an isosceles or like an equilateral triangle has 3 acute angles smaller than 90 degrees, or 2 acute angles and 1 obtuse angle, meaning two that are smaller than 90 and 1 that are bigger than 90. So those are the 2 types of triangles that you'd see. And if they don't have a 90-degree corner in them, then these rules apply. So here's an example. If A equals 50 degrees, capital letters talk about corners. So if this corner right here is 50 degrees, capital B, that's the corner B, is 30 degrees. And side B, notice this is lowercase b, lowercase letters represent sides, is 7 centimeters. Then, can we find the rest of the missing parts of this triangle? Well, yes we can. First of all, I know that if I take all 3 angles in any triangle and I add them up, so corner A plus corner B plus corner C, I'm always going to get 180 degrees. So it should be easy for me to figure out what corner C is by substituting those 2 in. So these 2 give you 80 degrees. If I add corner C to that, that gives me 180, so obviously corner C is 100 degrees. I like to go ahead and label each one of these back on my triangle as I get them so I know when I'm done. Okay, now we're going to have to rely on our law of sines to find the other missing sides. Notice that I have 1 pair of values that will give me 1 whole fraction. I have side B and corner B. That means that it would be a good idea to choose this formula, little b over sine of angle B, and then either one of the other 2 will work because I have both of the bottom corners, or corner A and corner C. So I'm going to try to find side A right now. So if I find side A, I would choose to use this. Okay. Now, why did I set it up the way that I did? Because in all 4 of these values, I'm only missing 1. I'm only missing side A. I have both of these angles, and I have this side. And that's what you do when you try to solve an equation. You try to set it up so there's only 1 part that you don't have. Okay. So, if I start substituting here, side B is 7. That's over the sine of 30 degrees. And that equals side A, which I don't know, over the sine of angle A, which is up here, sine of 50 degrees. So, what I would do is I would multiply on both sides by the sine of 50, or I could just find all the decimals and cross-multiply and find A. One way or the other, I would get A being approximately 10.72. So again, I like to label everything. So side A equals about 10.72 centimeters long. Find this number, sine of 50 degrees, multiply it by 7, divide that by the sine of 30 degrees. Would look like this. Sine of 50 degrees Oops, I have this in radian. Change my mode to degrees again. There we go. So the sine of 50 degrees is that decimal. That's this number. Multiply that on both sides to cancel it over here. So I'd multiply it by 7. Okay, and then I'm going to divide that by the sine of 30 degrees. Okay, so that's how I got that. Okay. All right, then the last thing I would do is I would find the third side. Now, can I use the Pythagorean theorem to find the third side? No. The Pythagorean theorem only works with right triangles. It does not work with a triangle like this where we don't have a right angle in the corner. Okay? So be very careful when you choose to use the Pythagorean theorem because it must only be used with right triangles. Okay. So what we can do now, obviously the only thing we're missing is side C. So obviously I'm going to choose this formula, C over sine C. And then I can do one of two things. I could set it equal to this one, or I could set it equal to this one, because I have both of these numbers and both of those numbers. So it doesn't really matter. I'm going to set it equal to B over sine of B. So, okay, side C I don't know. Sine of corner C, so that would be sine of 100 degrees. Side B is 7, and corner B is 30. Okay, so I'm going to find the sine of 100 degrees. I'm going to multiply it by 7 and then divide by the sine of 30. It's basically just like multiplying both sides by the sine of 100 degrees, and that would cancel on this side, which would give you your C value. All right, so sine of 100 degrees, sine of 100, multiply that by 7, and then divide by the sine of 30, divided by sine of 30. Oops, see how I divided that twice? I didn't mean to do that. There we go. Enter. Okay, so I get 13.79. And this is, again, is just an approximation since I'm rounding it off to the nearest tenth there, 0.79. And that's the last side that I need to find. And there you go. That is the first example of how to solve an oblique triangle.